Good day, dear ladies and gentlemen. I present to your attention a report on the theme Development of a Theoretical Foundation of a Controlled Synthesis of Multifunctional Coatings by Micro-Arc Oxidation Method. Micro-arc oxidation is a promising and rapidly developing technology that allows to give a high operational characteristics, micro-hardness, wear resistance, corrosion resistance and biocompatibility to the surfaces of valve metal and alloy parts by plasma chemical deposition of oxide coatings. The sphere of this technology is very wide, which in the future can lead to a great demand for products with micro-arc oxidation coatings among citizens of not only Russia but other countries too. Obtaining products with micro-arc oxidation coatings on an industrial scale requires the development of optimal technological regimes that guarantee a high quality of finished products with minimal cost for their production, which is associated with some difficulties. Firstly, there are large numbers of heterogeneous factors that simultaneously affect properties of formed oxide layer. Secondly, many possible applications with different requirements to their properties of the finished coating. Thirdly, insufficient knowledge of the micro-arc oxidation process, the lack of analytical description of some patterns between influencing factors. And fourthly, the imperfection of technological and measuring equipment, the inability to register and control the properties of oxide layer in the process of their formation. To solve this problem, in the framework of this study, a methodology for controlled synthesis of oxide layers, including mathematical models of micro-arc oxidation process and methodology for selecting the optimal technological parameters, was developed, and the principle of the prototype of an intelligent control system was described. The mathematical models considered below are designed to solve both theoretical and applied problems. The first model includes the micro-arc oxidation process model based on the equivalent electrical circuit, the second based on a graph theory. The information of micro-arc oxidation coatings occurs in a two-electrode galvanic cell, which can be represented in the form of equivalent electrical circuit shown on a slide. The initial stage of micro-arc oxidation process, called anodizing stage, can be divided into two stages. At the first, a dense aluminum oxide barrier layer, characterized by the resistance RPL and the capacitance C coat, is formed on the anode. At the second stage, a porous layer with resistance RPL is formed and the coating capacity is the capacity of the series connections of the capacitances of the barrier and porous layer. At the sparkling stage, an anodic oxide film is broken and microdischarges, which are characterized by the resistance RDs, appear on the surface of the part. With an increase in power of the microdischarges, a phase transition of amorphous alumina to a crystalline modification called corundum occurs. The higher the proportion of the corundum in the coating, the better are its mechanical, chemical and electrical characteristics. With an even greater increase in power of the microdischarges, the coating will be destroyed. During the study, expressions to determine the parameters of equivalent electrical circuit, such as resistance of the coating and microdischarges, were obtained by the use of Kirchhoff's law. This is taken into account the possibility of measuring the current, voltage and capacitance of the coating and micro-arc oxidation process. The obtained expressions make it possible to determine the thickness of the coating and the power of microdischarges, respectively. A generalized mathematical model of a micro-arc oxidation coating formation, which allows to obtain a fairly complete analytical description of physical phenomena in the micro-arc oxidation process, was also developed. Consider the main provision of this model. Firstly, on the basis of previously given equivalent electrical circuit, the expressions from 4 to 9 for the impedance of the barrier and the porous coating layer, by which it is possible to calculate the coating thickness HPL of T and HPL of T at the corresponding stage of the anode stage, are obtained. These values can be also calculated using the Faraday's law according to expressions 10 and 11. Surface and bulk porosity of the coating at the anode stage is calculated based on a geometric consideration according to the Keller's model. Based on the available empirical formulas and piecewise linear approximation of the experimentally measured time dependencies of the forming voltage, called forming curve, a recursive algorithm that allows to calculate the thickness of microarc oxidation coatings at the stage of microdischarges starting from the sparking stage is obtained. The forming curve of the microarc oxidation process is presented on the slide. Regions 1A and 2A on the graph corresponds to the anodizing stage. Regions 2 and 3 correspond to the stages of spark and microarc discharges. Point A corresponds to the beginning of the porous coating layer formation. Points B and C to the beginning of the sparking stage and microarc discharges respectively. The breakdown voltage UCR of I equals UCR of 0 determined at point B of the forming curve, and the initial value of critical thickness HCR of I equals HCR of 0 found from the expression 13 serve as initial data for the calculation. These values are substituted into expression 15, according to which the thickness of a microarc oxidation coating is calculated until the next break of the forming curve, point B1. From now on, the value HCR of I plus 1, which is taken from the previous iteration for point B1, and the voltage UCR of I plus 1, found at the point from the forming curve, are substituted into expression 15. Thus, the value of the microarc oxidation coating thickness at the stage of microdischarges up to the arc 1 are determined. Expressions for some characteristic of microdischarges, such as minimum microdischarge current in a single pore and the length of the discharge channel at the beginning of the sparking stage, were also obtained. To establish the relationship between the parameters of a microarc oxidation process and the properties of oxide coatings, a model based on a graph theory was developed. All factors of a microarc oxidation process, taking into account their influence on each other and on the properties of a formed oxide coatings, are shown on the oriented graph. The decoding of directed graph vertices designations is presented in the table. All the parameters of microarc oxidation process can be divided into three sets. Parameters effects, set V, parameters reactions, set R, parameters that are both effects and reactions, set VR. The relationship represented on the oriented graph can be analytically described as a system of equation 18. Each equation shows the change in the parameter reaction due to the combined effect of different parameters' effect on it. Of microarc oxidation process are expressed through a partial derivatives of a parameter effect by a corresponding parameter reaction. An example is shown on the slide. Taking into account the fact that some technological parameters are sought to stabilize in production, the system 18 can be simplified. The analysis of the system 19 showed that the all parameters reactions characterizing the properties of the coating depend only on three parameters effects: current density, processing time, and forming voltage. Within the framework of the graph model, expressions for calculating methodological errors in determining the properties of coatings arising from the instability of technological parameters, for example, electrolyte temperature, presented on the slide, were obtained. Regression models of a relationship of various parameters effects from parameters reactions were also obtained on the basis of available experimental data using the StatGraphics program. Some regression equations are shown on the slide. Based on the model 18 and the obtained regression equations, a methodology for selecting technological parameters for producing microarc oxidation coatings, with the help of which the optimal technological mode for forming a wear-resistant coating with a thickness of 100 micrometers with minimum porosity was developed. The parameters of obtained technological mode are presented on the slide. Obtain experimental data on the relationships between the parameters effects and parameters reactions of the microarc oxidation process. A working prototype of an intelligent automated system for the controlled synthesis of microarc oxidation coatings was developed. The appearance of the prototype is shown on the slide. The MIO Lab automated laboratory installation consists of a technological current source, a galvanic cell, a switching unit, a measuring board, a power supply unit, a microprocessor module, and is connected to a computer through a COM port. A galvanic cell is a 1-liter capacity filled with an electrolyte, in which there are 2 electrodes, an anode and a cathode, and the oxidized part is connected to the anode using a special mount. The galvanic cell has a protective fence in form of a magnetic switch, a reed switch. The measuring board includes a set of measuring transducers on the following values: current and voltage in the galvanic cell, the impedance of the formed coating, and the temperature of an electrolyte. The measured impedance values allow to calculate the resistance and capacitance of the coating, which makes it possible to determine the thickness of the oxide layer at a given time. However, since the impedance meter is connected to the same contacts as a technological current source, the microarc oxidation process has to be interrupted periodically, for which a switch unit is used. The microprocessor module is designed to communicate with the computer, receive and transmit measurement information from sensors, and ensure the operation of its hardware is an automated laboratory setup, including the warning signal for the operator. Technical characteristics of a developed device are presented on the slide. The software of the automated laboratory installation MIO Lab performs the following functions: hardware management, receiving, transmitting, processing and displaying measurement information, calibration of measuring transducers, output of the diagnostic messages for the operator. Data exchange between the installation and the computer is carried out through the COM port in the form of packets of a given size of 256 bytes, with the help of which control commands are transmitted and measurement information is received. The controller controls the electronic components of the actuators and measuring transducers of the installation and sends the measurement results to the computer. The appearance of the program interface is shown on the slide. In this figure, several functional areas can be distinguished: connection area, area for setting operating modes, oxidation and impedance measurement, graphic display area of signals, area for controlling the graphic display of signals, area of oxidation parameters, impedance measurement parameters area, electrolyte temperature display area. The device allows to receive microarc oxidation coatings in the anode and anode-cathode mode, measure current and voltage in a galvanic cell, as well as coating impedance and electrolyte temperature in real time, with saving the measurement results into a file for external processing. Display current and voltage waveforms, forming curve, current voltage characteristics, as well as amplitude frequency and phase frequency characteristics of a galvanic cell in the parallel equivalent circuit. Calibrate the integrated measuring transducers. At present, the developed automated laboratory installation MIO Lab is used to conduct experimental studies to identify and analytically describe the dependencies of parameters reactions on the parameters effects of a microarc oxidation process. A more detailed descriptions of this study will be given in a published article. The proposed theoretical principles and practical techniques make up the methodology of controlled synthesis, a powerful tool for studying and ensuring the controllability of microarc oxidation process. The obtained regression equations and mathematical models make it possible to predict changes of the oxide coatings properties in process of their formation, as well as to take into account their measurement errors caused by the instability of technological factors. Based on a developed microarc oxidation installation, an intelligent automated system for the controlled synthesis of microarc oxidation coatings will be created. The proposed models and experimental data will be used in the development of an intelligent application of controlled synthesis of oxide layers and entered into the knowledge base of this system in order to external improvement. Thank you for your attention.